Let's see the acidity of phenol, and we're going to compare the acidity of phenol with water and methanol, or you can say that we're going to compare the acidity of the following ions, which are phenoxide ion, which we get from phenol, hydroxide ion, which comes from water, and methoxide ion, which comes from methanol, right? So one thing we have to keep in mind is that alkyl alcohols like methanol, ethanol, etc., they're neutral. But right now we're just going to compare their relative acidities with water and phenol, right? And over here we can see that the most acidic is phenol and the least acidic is methanol, right? And another thing that we need to know is that acidity depends on the degree of dissociation. So if the dissociation is more, then it's going to be more acidic. For example, let's see HCl, which is our really common acid, hydrochloric acid, right? It can dissociate into hydrogen ion plus the chloride ion, right? But if you were to see C2 if you were to see an organic acid, which is a carboxylic acid like CH3COOH, right? This over here is ethanoic acid. It is also going to dissociate into this hydrogen ion plus this ethanoate ion, but we say that hydrochloric acid is a strong acid because it readily and completely dissociates and ionizes when it's dissolved in water, whereas ethanoic acid does not completely dissociates or ionizes when it's dissolved within water. So we have something like, instead of this arrow, we have something like this sign of reversible reaction present over here. So we say that it's a weak acid because the degree of dissociation over here is comparatively less. Now let's go back to the ones that we were discussing. Now, in phenoxide ion, we have, obviously, along with phenoxide, we have hydrogen positive, again, hydrogen positive, so let's start with the phenoxide ion. In the phenoxide ion, the negative charge which is present is not only present on oxygen, but it covers the whole of the ring. Okay, so it's like kind of integrated within the pi system of the ring. So this negative charge is actually covering this whole area, right? So when this negative charge of magnitude 1 is covering a much larger area, so that means the electron density or the charge density over here is less. The charge density over here is less because the charge is spread over a larger area. That's why this hydrogen ion and this phenoxide ion, they won't be attracted to each other that much. So whenever we have phenol, the oxygen and the hydrogen, they're not that attracted to each other. So there is a much larger possibility that it's going to dissociate. It's like much easier for the hydrogen and the oxygen to dissociate into ions. So that's why it's the most acidic over here. And if we are to see the methoxide ion, this methyl group, which is an alkyl group attached, it has a positive inductive effect. Okay, so that means that this methyl over here is going to contribute to the charge of this negative on top of the oxygen. So that means there is going to be a very high charge density on this oxygen. So the charge density over here is going to increase, which means that the hydrogen and the methoxide ion are going to be attracted to each other. So the degree of dissociation is going to be less. That's why it's going to be least acidic. Now let's review whatever we have discussed, and it all boils down to the fact that the most acidic ion is the phenoxide ion and the least acidic is the methoxide ion because of the relative charge densities. There is less charge density on the phenoxide ion. That means that it has higher degree of dissociation and thus it is more acidic, and acidity depends on the degree of dissociation. The more dissociation we have, the more acidic it's going to be.